Welcome to the Explainer. Today we are diving deep into one of the biggest questions out there. What is everything actually made of? We're going to do that by tracing the incredible and kind of wild evolution of how we picture the atom. So what does an atom really look like? It's a question scientists have been wrestling with for centuries. And as you're about to see, the answer isn't so simple. In fact, it has been a moving target to say the least. Our journey is going to take us through more than a century of mind-blowing discoveries. We're going to go from a simple, solid sphere all the way to, well, a fuzzy cloud of probability. And trust me, each step along the way got stranger and stranger. Okay, here's our game plan. We're going to tackle this story in 5 key stages, and you'll get to see how each new model was really born from the problems of the one that came right before it. All right, let's start at the very beginning. Part 1, from indivisible to divisible. This is where the whole scientific story of the atom really kicks off. So, way back in the early 1800s, a guy named John Dalton came up with this idea. He said the atom is the end of the line, the ultimate, smallest bit of anything, a fundamental particle you just couldn't break down any further. The best way to picture it? A tiny, solid, unbreakable marble. Simple. Well, that simple idea ran into a big problem. By the end of the 19th century, scientists started discovering things like the electron that were even smaller than atoms, and that threw a huge wrench in the works. Suddenly, Dalton's simple little marble had to have parts. Things were about to get a lot more interesting. So, the discovery of the electron completely smashed that old model. Which brings us to part 2, the plum pudding atom. In 1898, J.J. Thomson gave us our first real glimpse inside. So, Thomson imagined the atom was this sphere of positive stuff. You can think of it like a ball of cookie dough, and the tiny negative electrons were just kind of dotted throughout, like chocolate chips. The popular name for it back then was the plum pudding model.
Okay, so if the atom is really this soft, squishy cookie, what do you think would happen if you shot tiny little bullets at it? You'd expect them to just zip right through, right? Well, a scientist named Ernest Rutherford thought so too, and he set up an experiment that would put this whole pudding idea to the ultimate test.
And that leads us to section 3, the discovery of the nucleus. Let me tell you, Rutherford's experiment didn't just tweak the old model. It blew it completely out of the water. The results were just bonkers. Most of the particles shot right through the thin gold foil, just like he expected. But every now and then, one would bounce straight back. Rutherford himself said it was as incredible as if you fired a cannonball at a piece of tissue paper and it came back and hit you. There was just no way the plum pudding model could be right. The atom had to be mostly empty space, with something incredibly tiny and dense at its core. So just look at this shift in thinking. It was radical. We go from a model where everything is spread out and mushy to one that's basically a miniature solar system. You've got this tiny, dense, positive nucleus where all the mass is, and the electrons are orbiting way, way out in the distance. A total transformation. But there's always a but, isn't there? The physics of the time, what we call classical physics, had a massive problem with this new model. An orbiting electron should constantly be giving off energy, which means it should spiral down into the nucleus in a fraction of a second. Rutherford's atom should instantly collapse. So why doesn't it? Why does matter even exist? To fix this huge collapsing atom problem, we now turn to part 4, Bohr's revolutionary orbits. A Danish physicist named Niels Bohr came along and basically said, okay, the old rules are broken. We need new ones. Bohr just threw the old physics rulebook out the window. He proposed that electrons can't just orbit wherever they feel like it. They're stuck on specific paths or energy levels, kind of like rungs on a ladder. They can't exist between the rungs. And to move from one level to another, they don't spiral. They just jump instantly. He called it a quantum leap. It was a totally wild idea that broke all the rules, but hey, it worked. It explained why atoms are stable. But of course, the story doesn't end there. Bohr's model was brilliant. For hydrogen, the simplest atom there is. The minute you tried it with anything more complicated, the whole thing fell apart. Plus, it clashed with other new weird ideas popping up, like the Heisenberg uncertainty principle, which says you can never know exactly where an electron is and where it's going at the same time. Bohr's model was a crucial step, for sure, but it wasn't the final answer. And that brings us to the final chapter, section 5, the modern quantum cloud. This is where things get really, really weird, because it required everyone to completely rethink what an electron even is.
Yep, the biggest change of all was still on the horizon. In 1926, an Austrian physicist named Erwin Schrödinger developed a mathematical equation that would completely redefine the atom and become the very foundation of modern quantum mechanics.
So here's the deal with Schrödinger's equation. It stops treating the electron like a tiny little ball, and instead, it treats it like a wave of probability. The equation doesn't tell you the electron is right here. Nope. Instead, it gives you a probability map. It tells you where you are most likely to find the electron if you go looking for it. And this right here is the absolute key. We have to throw out Bohr's nice, neat idea of a 2D orbit, like a planet's path, and replace it with a fuzzy 3D orbital. It's not a path, it's a cloud, a region of space where the electron probably is. We have to give up knowing for sure where it is, and instead embrace the probability of where it could be. So our modern picture is this incredibly rich and complex structure. You have main energy levels called shells. Within those, you have subshells, and the subshells are made up of these different shaped orbitals, these probability clouds. And the amazing thing is, this bizarre, fuzzy, probability-based model, it works perfectly. It predicts everything from how atoms make light to how all of chemistry happens. So when you step back and look at this whole journey, what does it all mean? Well, it shows that science isn't about one person having a single eureka moment. It's a process. It's about building on ideas, making mistakes, and constantly refining. Every model we saw solved one puzzle but created a new one. To really understand the atom, we had to let go of our everyday, common sense intuition. And that leaves us with one last, really exciting thought. This whole transformation from a solid little ball to a ghostly cloud of chance happened in just over 100 years. It really makes you wonder, what's our picture of the atom going to look like in another 100 years? What new secrets are we going to uncover? One thing's for sure, the quest is far from over.